Hello, this is Schwab again. This time I'd like to show you very interesting new features which were added in version 6.9, and this is a way to parametric entry of data and parametric editing. We call it sometimes polylines because we do the parameters by editing the polylines. I've prepared here some geometries. We start with an empty project here because I'd like to show you how these polylines work on a 2D meshes. Uh, First, let me make a basic 2D mesh, a very simple one. And when we're editing the path lines, it will be very useful to use working planes. Well, the working planes with 2D meshes is just the plane in which the 2D mesh is defined or 2D grid is defined. So we have it very easy in this case. When we want to define any parametric geometry, we need to have some elements. So let's make the elements, and I will just make one quad. Right, I do it exactly right at the beginning, at the origin, and it's 1 times 1 in millimeters. And now we can simply say dialogues and do here the polyline. When you open the polyline dialog, it will automatically understand that you want to see the polylines. If I show you the polylines, this is the polylines really, right? You see the red line and the blue line. Those are two polylines. And you see here is the number of polylines which we can use. This is polyline number 1, the red, or 0 if you like, and 1 for the blue. In this case, we have a XY mode, so we're defining in X and Y. The polylines are always defined in two variables, in two coordinates. But these coordinates can be different. Z, A, X, we have different modes, and we will go slowly by all these modes. But let me first explain it on the standard XY mode. When we define XY mode, this X1 simply corresponds to an X coordinate, and X2 corresponds to Y coordinate. So we see now, first polyline, the red one, this is the current point. Maybe I can get rid of the coordinate cross. Okay. And we can move it backwards, we can move it forward, or we can move it down, or we can move it up. So we can define the X, Y, Z coordinates. And we can also advance to the next point, this one, or we can move to the upper polyline. And now this is the first vertex, and this is the second vertex. When you want to map any geometry to those polylines, you want to make it parametric, it is using a mapping. So you need really to say, I want to map that element. That is done here. Assign. We can assign either selected entities, or we can assign what is inside that rectangle. So if I just say assign inside, now my element is hopefully assign. It is because this button appeared. So I can say show assign. You see those red points are really points of the grid, and they were highlighted because they're really linked to this quad. Now if I deform that quad, I will be moving also that brick. So that is all about parametric entry, about polylines editing. Okay, I can just hit escape to highlight those points. And now, even if I save and reopen this project, these corners are already linked to that polyline. Okay, I can again reopen that polyline, and now it is already linked. So it's very easy for me to say, let's say for the polyline number 1, which is the blue one, I can increase the gap like this. And when I say apply mapping, it will now remap that element into my polylines, into my new change rectangle. Okay. We can also change the other coordinates, for example, like this. And whenever I say apply mapping, it just goes there. Now, I should also explain what you're seeing here. First of all, you have the one polyline and the other one polyline, and they are forming a rectangle. But there is a connecting line in between. You see, when I'm moving this slider, that shows me a relative coordinate position on both of these polylines. So if I want to have like 0.25, this is the relative 0.25 on this one, 0.25 on that one. This gray lines, they're showing me at the nearest projected point, or connection to a nearest projected point on each polyline. That is used sometimes to estimate the thickness, the gap, when you're doing some shell calculations. And we can also use this advancing slider to insert new vertices for each of those polylines. Okay. Now let me just edit some polyline at the bottom. You should make sure that you don't swap the lines like this. You see, I did swap. I moved this point, which was originally here, over there. So now the element is swapped. And if I just say apply mapping, the program can even crash. Be careful on that and don't do it. Put this back. You have to move this point instead. So we have to really be very careful when we applying any mapping, right? Why? Because applying mapping can move the nodes, can collapse the elements, and you can get a geometry which is not compatible with the requirements of the non-zero area elements, etc. Also, we have here an ability to change, let's say, the angle of these entities. You see, I can very easily change the arc, which is there. It was originally 0, now it's minus 62. If I move to the second one, I can similarly deform this, or I can do it the other way around. And now, of course, my mapping is very different. So it's not rectangular anymore. And I can just say apply mapping and nothing happens. Why? Because this is only one element. Well, what if we try to split it into more? So let's do. We can say show me boundary edges. And now I can say split this one, that one, this one, this one, that one, that one. And now when I say apply mapping, it will automatically apply to this to the polyline shape. Now again I can refine even more and I can say apply mapping. So now I'm getting a geometry which is matching those polyline shape. And again, if you just decide to change it to the shape, you can just say apply mapping and you get very different shape. So you see we have a parametric entry of the geometry. Okay. For now, let me just close this. If you are editing and applying mapping to a 2D mesh, which is basic, well, here we have requirements that the nodes cannot be occupying the same position, the elements can't be swapped, etc. But we have an advantage that when we convert it to 2D mesh, which is for solution, we don't do any checks over there, right? We just accept any elements. So now it will be much easier for me to work with those polylines, and I don't need even to worry about, let's say, swapping the elements like this, even though it's not correct, but it's a temporary position which I can get out and I can apply mapping again. So with the solution meshes, it is even more easy to edit those dimensions. Of course, if you resolve something what is not correct, you get wrong results or you can get crashes in the solver. So be careful on that. We also can do lots of definitions here, define lines, define tangents. We can either catch the existing points. For example, if I just have here some kind of core nodes, I can catch them, or I can very easily edit those pathline by just checking for the working plane. So if you just say define, I'll be adding positions here, there, there, there. And if I just right click, I apply mapping, it shows me a new shape. Of course, that is relatively weird shape, so I should not do that. I can also remove vertices. When I apply mapping, I'm back at the original shape. We can also do tangents. We can define tangents. So we do it like this. When I make a new point, you see it's creating tangential projection and it always creates an arc which is tangent to the previous one. And if I don't like it, I just escape and then I apply mapping and I can get very curved shape. Again, the same thing I can do here for this polyline. Define tangent and just do it, let's say this way. Okay, so by this thing I can create very curved and parametric geometry. Well, we are not interested really in doing this kind of thing, so we can just close that and we can apply something more reasonable. I have prepared here a very typical example of what we're trying to solve. You see, when we have, let's say, geometry like this, which is a kind of distributor which is preparing the flow for a wire. Well, we can see here that the flow over there is more or less not influenced by the distributor because first of all, this is consuming a lot of pressure. Second, that's too long to have any effect on the previous geometry. But we probably can mimic only, let's say, this parallel part in 2D Fab. So if we decide to do that, we can certainly go to the dialogues and say, I want to import a DXF from a CAD. I've prepared here already a DXF which represents the inner part, and I've prepared also the XZ which represents the outer part. Here they are, right? And now I can say only apply mapping, and you see our geometry has been just applied because it was originally a quad. It has been applied to this shape. Let me just convert this back to a basic grid, because if in the basic grid I can really split the elements more. So I could be splitting these and I can get much smoother shape. Apply mapping, and you see we have it straight. Now we can see that here we don't get right the point in the corner. For that purpose, we have here the ability, we have to of course find that corner first. So it's polyline, red polyline is polyline 0, vertex 0, this is 1, this is vertex 2. And we can say the local coordinate is not, it is in bracket, means it's automatic. But if I can just move this way, and then when I apply mapping, you see it will be changing. This, apply mapping, okay? And then we can very easily just split this element here. And when we say apply mapping, we get that corner nicely filled. Of course, it depends on the mesh density, how well you cover that geometry, okay? We also need to see that here we have a radius. This DXF came with the radius for the second polyline. The blue polyline has a radius over there, so which can be adjusted. But we can, of course, to cover that radius, we need to bring here more elements and just split them into many, and then apply mapping, and we get a very nice round shape. You see these elements also here are relatively squeezed, or stretched. So we can influence that again by this local coordinate here. So typically we need to put the local coordinate to a node. I would do it by, let's say, moving on the polyline 0. I can move here and say at this place I want to insert a new vertex. This is the one, and for that vertex I will change my local coordinate. When I say apply mapping, you see these elements are rearranged. So you can see also that the mapping influences, or local coordinate influence, the way the elements are created. Okay. Now, as you can see very easily, from one rectangle we've created a very complex mesh which you can now rotate, revolve, and use for either planar calculations or really for some, with the revolved case, for the 3D finite element calculations. Okay, so this is what the polyline parametric entry is for, and there is a lot of functionalities which we will slowly reveal and explain to you. Another possibility how to use these things is really in the 3D shape. Here I have a geometry which has been already described here. That's the one, and we only kept there the base, right? This is the base, and I here have a small ring on the top, okay? And I'll be trying to map that ring to something what can be parametric, to do some mapping on that ring. Okay, for that I will highlight these points, and I'll know that my uh, angle 0 is over here. This is minus 90, this is plus 90 in the coordinate system. If I show you the coordinate system, you see this is the x coordinate. So we really need to pick these points for the definition. And if I go dialogues polyline, first thing I need to choose the cylindrical mode. Okay, and now I will say define the vertices, and I will pick these vertices. You see, we have here two rows of elements, in fact. One at the bottom I will not touch. The other one will be used for the whole definition. Okay, and if I just say assign selected, hopefully he has assigned all these nodes to the mapping. Let's see. Yeah, well, you see we have all the nodes assigned. We can even see that at the bottom plane we have them assigned. Okay, now I hit escape to highlight them. So now all the points are assigned, and now we could be changing those Z and alpha coordinates. This is Z, and this is our R coordinate, Z and R coordinates. That means we can move them forward, for example, like this. And when we say apply mapping, it will just automatically adjust. Okay. I've prepared here now just to be able to get those right dimensions. I've really used I keep here a tip, this thing here, which was obtained from the previous geometry. So let's get those points from here. For that purpose, I will just show for the tip the corner points, and I'll put them to my clipboard. So I go operations and I say copy to clipboard, and I will use I need to take the alpha 0, that's the one. So I want this point, I want this point too, this point, and also on the other side, that point here, that point here. That's it, close. So now they're in the clipboard, and I can put them here. These are my points, and I will just use them for the definition of those polylines. So I will just say define. So we just say define, and we will use that point here, that point here, and this last point. That's enough. And for the second polyline, we will define this point, that point, and the last point here. Okay, we have our definition. You can see that we've defined two polylines, and they're coming through here. We have a little problem there because when we're moving, the edge gets across the corner here. So we probably, for this particular corner, which is on polyline 0, this one, we need to change the local coordinate, okay? And then we can apply mapping. See, now my whole mapping has been made. Of course, we don't like it. We don't like the mapping. Why? Because we have only one element across. So we need to really now go and change the division. So we will be now splitting those elements. Okay, once we're happy with the splits, we can stop the splitting operation and we just say apply mapping. And now we see that we already start to get the dimensions we'd like to have. We can also see that for the here we may need some small radius, so we go to polyline number 2 or numbered labeled 1, and we go to the appropriate point, which is the one here, and we say, okay, the angle will be a little bit bended like this or more, okay, and then we can say apply mapping, and we see that it really adjusts to that radius. We start to have the shape we want. Of course, we don't have the shape correct over here. We can solve it either by changing the local coordinate of this point, or we can change it by extra split, and we do apply mapping again. So now we get finally the shape which was appropriate to what we'd like to have. We also don't like the fact that these elements are not nicely aligned with the perpendicular to the geometry, so we may influence it by adding one more point to, let's say, coordinates here, and we insert point to this position, and for that point we can change the coordinates, and when we say apply mapping, we will see that we have changed the alignment over there. We still have some different alignment there, but it's okay for the solution. Now, that was a very easy way how to define the geometry. Maybe you find it complicated, maybe not. The only thing you need to do now is just click on the base and take them together and simply solve them together, because they really are matching, they are conform. So when you start the solution with the interface in between, you get a very perfect solution. There is another possibility that you just copy for merge this one and then paste it from clipboard to that one to get it again one mesh. But then you lose the mapping, right? Now also the main advantage here is that we still keep the mapping anytime forever, and we can always adjust the mapping again. So if you just want to change the gap, no problem. You can change the radius, you can change the parameters. So the only thing you need to do really here is to, let's say, open that, well, I don't know, 1.2, and then also for the last one, you may do this to, let's say, 0.6. Okay, and when you say apply mapping, you just deform the shape to match those dimensions. Okay, and then you can resolve and see if there is any effect. So it's very simple to have a parametric entry. We can also use that parametric geometry for cases like flat die, where this is the original flat die, and we can again from the flat die keep only the base, which is this thing here, and we can have on the top the lips, or we can just keep this one only, which is a very thin element here. I've already defined here a basic initial rectangle, and when we say assign inside, you see that all the points are really assigned. So now we can only define how that changes, and we can give really arbitrary shape to these polylines. Again, I've already prepared those. I will not now import the XF, but I can show you a different way. We can edit those polyline. Okay, so now I'm editing the red one, the polyline 0. If I go to my folder, I have here a flat die txt, which is having for the inner already the prepared definition. So I can just put it here. Now the definition always contains the Z position, the Y position, or the X1, X2, and then the next one is the bulge, and then the local coordinate. This is 0, 1, so that was very simple. But for the second polyline, we'll use something a little more complicated. We have here more points, which will define the relaxation chamber. And when I say apply mapping, again, I have only one straight element, so it looks like that this is not working, but now we can very easily go and split it into more sections. And once we're done, we just, by apply mapping, will come exactly to the shape we want, okay, for the relaxation chamber. And now if I mirror this, you will see that this is really coming very well with our base, and now we can solve it as it would be one geometry. Again, we gain, the main power is that I can anytime change the ellipse, I can change the length, I can change the radius here, whatever I'd like to do is really parametric. Okay. Another possibility how to use the parametric design is to use it for, again, for spiral mandrel dies. This is a conical die with periodicity. This is my periodicity, right? It's really periodic geometry. And I've built here a small ellipse on the top. This is the ellipse. And very easily, again, similarly as I did it before, I can use here simple two lines. I can assign whatever's inside. And now I can simply stretch them, deform them any way I like. So let me just make this taller and smaller diameter, right? The next polyline will be also, can do something like this, and then I will add a node to here, add a node to here. That's enough. And for this one, I will again add a node. Okay, that's it. And I can add some radii. For this one, for example, I will use a radii, bring it there. I'm happy with this shape, so well, that's my final ellipse, right? Whether you like them or not, it's not important. We just want to show the principle. And when I say apply mapping, it will move there. Of course, that is not what we want. Again, we need really to split that. So let's do some splitting. And then we call again the polylines because it really remember. And we finally have the shape we want. We don't like the fact that the elements are so squeezed here there. We need to adjust the local coordinate for this point like this. When we say apply mapping, we have a very nice alignment of the elements, and we really start to be happy with this mesh. And then when we decide to make it periodic, we'll get our annually the way we want. So this way you keep it again parametric. We also have other options for the helixoid calculation. We were using here the rain pipe, the drainage, and we've seen that this is mirrored. And we also know that here we don't have a very simple definition in the shell model, and that's simple line and then some elements. Well, these elements, they have a certain thickness, and we could see that our final flow distribution, this is temperature, but the velocity is, we have more mass there than here. So we need to really compensate somehow, either by thickness or some other way, and we can now start to play with those dimensions. So I can very simply say I want to use the so-called connector mode. And this simple mode of polyline is having only one polyline, and you can define that polyline by picking one starting and one ending point, or I can go through several points like this. When I've done it, it will create the polyline through those points. So we have now several vertices there, and I can very simply go and specify what is the dimensions. Let's say for the gap, I have 1 millimeter for this node, and let's say 10 millimeter for that node here. And when I say apply mapping, it will simply use that thickness gradually from 1 to 10 on that length. Okay. Again, very simply, I can again restart that command and say I don't want 10. I want instead let's say 3. And then if I apply it here, it just does it for one point. By this apply, I really apply it to the whole all points on the polyline. Well, we do it only on that line. We don't do it here. Well, nothing's easier than to define another polyline. See, we don't need to have one set of polylines. Here I can add mapping. So I have now mapping 0 and mapping 1. I can choose again connector mapping. So I will do the similar thing. And I will define a new mapping from this point here to that point over there. And if I just hide those front faces, you'll see that my mapping is there, and I can start the editing of the gap, and I can just say, okay, this will be 3, that will be also 3, and I will do apply mapping. So I have 3 everywhere here. Here I have 3, here I have 1. So this is a way how to simply gradually open gaps and make linear transitions. There is also another possibility that I find the appropriate vortex which I'd like to change. For example, this one here. And I say here I will have a controlled local coordinate. By this I will tell that this polyline is split into 2 pieces. So now if I go and I said, let's say that this is 20 here. Okay. And if I just apply mapping, he will go from 3 to 20 and from 20 to 3. If I go 20 here, I'll say apply mapping, and he goes from 3 to 20 and then from 20 to 20. So that way I can very nicely control the thickness on those shell elements. Okay, and that's my final geometry. I know it's exaggerated, but I just wanted to show you the principle of editing the dimensions. Okay, so as we can see, there is a whole amount of possibilities. I'll show you now probably the last one, which is probably the most advanced, and that we can demonstrate on basic 3D element. We just need to create here 3D bricks. I just made them like this. Okay. And now we will go to dialogues, and we use a special mode which is called 3D Loft. This 3D Loft allows me to do very complex geometries from several steps. So now we have, you see, 4 polylines. So this is the one, that's another one, the blue one. This is number 3, this is number 4. you know, and it's labeled 3, but it's not, it's the 4th polyline. Now I can add one more layer here, see? So I have one layer, second layer, third layer, and they really going 1, 1, 1. But now I can just say assign inside, and these 2 bricks now are assigned, which I can again check by show assign. Well, once it is assigned, I can do an arbitrary deformation of these bricks. So for example, for the last 2, I will deform I will change the Z coordinate, let's say 50. This one will be also 50. For the third one, I will say this will be 35, and this one will be only 25. So now I have them like this, and when I say apply mapping, he will do kind of very stretched geometry. And now we have to slowly start to play with it. So first one will be, let's say 20, 20. So this is how we start. Then the next one will be maybe 35, and this one will be, okay, I've made the geometry like this. And now we can do, let's say, change of angle here. And when I apply mapping again, it's only one element, so I don't see anything. I need to split it again into many so that they can adjust. I start to see that my shape is already being deformed. I can go to this one again, change the right, and I see already here a quite interesting shape, and I can elaborate it the way I like. Okay. At the same time, of course, anytime you can change the Z position of these polylines. Every polyline has a small Z position, and you can adjust all the dimensions to whatever you like. Okay. Of course, you can insert points here and let's say change completely the shape. Simply, you can do arbitrary things, right, with any polylines. So we've seen that there's a big amount of possibilities with those polylines. Feel free to look at some of the other projects I'm doing, let's say the projects which is dedicated to profile dies, where I show how these polylines can be practically used.